Hi, here is what I promised Jen. So I'm going to run through this manually, but just for the residential side, not for the commercial side. Commercial side, we'll run through that in a session. It's so much shorter. There's only probably about 6 or 7 pipes, so I don't see a problem with that. Anyway, I've kind of added on to the spreadsheet. So what I've said is category 2 system. Density is 2.8 millimeters a square meter a minute. Duration is 30 minutes. 4-story, including the highest floor, including the ground. Sorry. Tank the highest range of sprinklers 11.1. That's the static head, hydraulic head. CPVC pipe's going to be used like virtually 99.9% of sprinklers in residential applications is CPVC. I've never mentioned it up to now, but it makes a difference, as you could imagine. CPVC is incredibly smooth, so it has less friction and offers the water less friction as it passes through, and hence reduces the pressure drop. We'll play around with those numbers and you can have a look at the pressure drop. That's why I've identified the pressure drop box there. So when I change that, you'll see the pressure drop increase. Anyway, as we said last week, the head operation. So if we look at that, and if you remember, here's our room, 27 square meters, but we'll be using more than 13.5 square meters for each head. So what's relevant is the distance between the heads and the maximum distance to wall. So if I go back to the account, so now that maximum distance to wall is 2.25. That effectively means that the sprinkler is dealing with 4.5 by 4.5. To check it against the maximum distance between the heads, that's only 11 square meters or so, which is less than half of the area of the room. So our effective coverage is 20.3. In our situation, the heads have been located symmetrically, so exactly the same. But don't be surprised when you see schemes. Here is one. Only you can see it, but I can't. Get that out of the way. But as you can see, there's a lounge diner, but there's a head there, and there's a head there. I would tend to put a little bit more there, but they haven't, and it complies position-wise. There's a principal bedroom, and again, nowhere close to being central, but basically that's the distance, 2.3. So the effective area will be 4.6 times 4.6 for that particular room. So don't be surprised if you see strange situations where nothing appears to be symmetrical, because for some reason, and when I speak to somebody who does this for a living, I'm sure they'll tell me why. So we've got that. We've got 20.3. Or 20.25, worked out the density there. The density that's required, the required flow through the sprinkler head is 56.7 litres a minute, and that's what should have been on there, but it wasn't. But that's exactly what it is. So what we've now got to do is, with a minimum of 0.5 of a bar, that's the least pressure any sprinkler head can experience in a 9251 compliant sprinkler system. What's really odd is 12845 only requires 0.35 of a bar, but that's that one. We're not looking at that one. So if we put the bar at 0.5, and if we use a commoner garden K70 head, which seems to be the most common go-to, it's actually 70.6. And what that means is it'll deliver 70.6 litres a minute of water at half a bar, at 1 bar. So if it experiences 1 bar, that's how much it will discharge. But it's not experiencing 1 bar, it's experiencing half a bar, and it will discharge 49.5 litres, which isn't enough. We need 56.7. So we need a bigger K factor. So we'll go on to, it's a little bit more specialised, but they are available. We'll go on to a K80, and that gives us 56.6. Now, the reason I'm going to still run with this is that when we get to designing the pump, there's no way that the pump will be bang on the money. The pump will deliver more water at a higher pressure than what the minimum will be. So I wouldn't worry too much, for such a small differential. If it was 60, I might say, oh, we might need to do something about that. So the likelihood is that the system will experience more than half a bar at that most remote sprinkler head. If I even put 0.51 in there, it will push us over the edge. So see that straight away, it pushes it over the edge at 57.1. And a lot of designers do that. They actually design on 0.51 rather than 0.5. Just because they know they're going to hit that pressure when they actually end up designing the pump. So now the first thing we've now got to look at, before we can look at the second sprinkle head, because the second sprinkle head theoretically will be the same, but it will experience more pressure. If I put an 80 in there, that will experience more pressure, and we're going to have a look at that now. So if we then go back to and we look at that, and this pipe is 3.3 meters long. So now what I'm going to do, I'm going to work out the pressure drop on that piece of pipe. And basically that will be the lowest, and the pressure experienced by each sprinkle head further down the line will be greater, because remember, this is the most remote head. Okie dokie, so that's 3.3, and we're going to start off with a 20 mil pipe, and you'll see why in a second. So if I say, right, there's a 20 millimeter pipe, the flow is, and we'll put the proper flow at 50. Oh no, we don't need to, because it's kicked in. There's that C value that I was telling you about regarding the value of the CPVC. If that had been steel, it would have been slightly lower. Now that gives us a pressure drop. That gives us a pressure drop at 0.046 of a bar. So if I now add that 0.046 plus 0.5, obviously that gives us 0.546. So for that second head will have 0.546 of a, and straight away you see that one's going to deliver more water because of that. Now what I said was we'll start off with a 25, but that's, sorry, it's 3 meters long. Let's start again. It actually, I thought it wasn't all that large. That's per meter. I forgot to put the length of the pipe in, which was 3.3, and that gives us a pressure drop of 0.152. Now that's if we keep using that pipe, it's going to have large pressure drops. What I'm going to do, I'm going to change that to a 25mm pipe. And all of a sudden now that drops down to something reasonable. And so that second head is 0.0551. That's why I didn't spot it straight away, because the numbers were about right. Okay, so that's that pipe. Now, the second pipe, if we now look, we've now got 56.6 going through the first head. We've got 59.4 going through the second head. That gives us a combined 116. So if we go back onto the AutoCAD, there's 56 going through there or so, and then through this pipe here, there is 116 or whatever it was. So now we've got to figure out the pressure drop on pipe 2. Now, what I've already done, so that's pipe 1, pipe 2, we're going to go up to 25mm. That design Q is flow. That's already been upgraded. Let's get that up to 25. Now we're just going to guess these distances, otherwise we'll be here all day. But I reckon that's probably 4 meters. So let's stick 4 in here. But what we've also got to do on that 4, is to we've got an elbow. What we'll do the far elbow on every pipe. So there's an elbow on there. So that gives resistance too. Now what this code does, in other codes I've seen you apply whatever the manufacturer's pressure drop value would be. But for this, they use this table sits in Appendix B. So we're on 25mm, and what it says is that if you've got a 90-degree elbow, it's going to be effectively the same as 2.13 length of pipe. So we've got a pipe in there of 4 and then 2.13. So that gives us 6.13 as the effective length of that piece of pipe when it comes up. Of that piece of, of that piece of pipe. So that's 6.13, which is 2.13, roughly 4 for that. Okay, so we'll stick that in the chart. So there's pipe 1, flat 2, and that is 6.13, wasn't it? So we're up to 0.358 of a bar. Okay, so now we're on to flat 3, pipe 3. Now pipe 3 has got, it's roughly again 4 meters, and it's got an elbow on there, and it's got a T there for a sprinkle head. So we've got an elbow, a T. Sorry, we've got 2 T's, a T there, and 4 meters of pipe. So if we nip onto here, nip onto this fella, got 4 meters again, but we've got 2 T's, and they're 1.52 for a 25mm pipe. So that was again 4, and we're going to use 1.52. 1.52. That gives us 7.4. So flat 2. So it gives us, number 3, flat pipe 3, 7.24, wasn't it? So you can see that the pressure, once you start putting fittings on, then the pressure starts to, now that word dim's gone in there, it just has. So that's the flat pipes done. So we've got a distribution pipe next, and we'll punch that up to 32. So we'll punch that up to 32. We'll get a dimension on that, because that is that. I'm going to guess that one, and that to that point there is 18.3. Now we'll put our 18.3 in. 18.3, but we're going to end up with some T's and all the rest that goes with it. So let's pop onto that. So we've got 1 T there, 2 T's, 3 T's, 4 T's, 5 T's. So let's go back onto this fella. 5 T's, T branches. Now we're on to 32, so it's 1.83, 1.83, 1.83, 1.83, 1, 2, 3, 4. And that gives us 27.45, 27.5. So let's stick that in our main distribution pipe. Did we say 27.5? And you can see, the pressure drop per meter. Well, I've gone too far, haven't I? Flat pipe flat pipe 3, distribution pipe 4. That's the one I was looking at. Was that 27.5? That's 32. It should be 6. Yeah, that's right. So that's what that one is. So you can see that those pressure drops per meter drop as the pipe size increases. Okay, so that's 4. Let's have a look at 5. I think 5 is relatively short. So it's probably, say, a meter and a half plus a T, because what that's going to take you on to, it's this pipe here. No, it's about a meter and a half and an elbow. What's that one there, actually, isn't it? Meter and a half and an elbow. So let's get on to that. 1.5 and an elbow. We're on 32, aren't we? So that's 2.44. Get them. That gives us 4 meters. Gives us 4 meters. So now the next thing we've got is the local risers with the valves, which effectively is that. So I'll take that all the way to there, to be fair. So basically we've got a flow switch, we've got a gauge, and we've got a flow switch, gauge, isolation valve, and a drain valve, and we can put that on a T. So we've got 2 T's, and those bits and pieces. So let's see what that gives us. It'll be 3 meters long, roughly. 3 meters long. We had 2 T's, if I remember rightly. So 1.83. So that was one for the drain valve and one to connect to the main riser. 3. Then on top of that, we had the floor switch, which is 4. We had it'll be a globe valve. I doubt it'll be a butterfly valve. I can explain that some of the time, but the butterfly, it's more likely to be a globe valve, but never know. So there's 13 to go into that, and then we had a gauge, and I don't think I've got anything for a gauge. I'll just stick one on for the gauge because theoretically it shouldn't provide too much resistance, and we'll round that up to 25. So we'll round that up to 25 meters. So now we've got the main riser. So if we look at the main riser, I'll stick a dim on that, and it would be from there. And we've already picked that T up, if you remember, and that's going to be to there. So that's 6 meters. So we've got 6 meters in length. Let's get rid of these fellas. And let's see what we've actually got on there. We've already taken into account that T. So we've got 1 T, 2 T's, and then we've got a T here to tee off for so we've effectively got 3 T's on there. So let's have a quick look at what a T will give us. We're on 32, T branch 1.83, should have remembered that, shouldn't I? 0.83, 1.83. So we're getting to 11.5 meters, getting to the point where we're figuring out, the kind of stuff and the kind of components that's offering a degree of resistance. So we've got 11.5 meters on that. So now we go from that riser through the plant room, which is pipe 8, which is that fella there. So we've already picked up that T there. So we want a distance on that, rough distance. I reckon it's about 9. Oh, 9.1. So, and then we've got 1 T, 1 elbow, as it turns out. 1 T, 1 elbow, and we're keeping in at 32. One T, 1 elbow, 9 meters. 1 T, already in there. 32 elbow, 2.44. 13.2, 13.5. You always add a few fittings in rather than be really economical with it, because by the time we finished all of this, we might have 20 T's and 20 elbows or something like that, but I'll guarantee we'll use more than that. So that's 13.2 for pipe 8, wasn't it? So pipe 8, 13.2. 0.23. Then we've got the plant room riser. That's going to be about 2.5 meters. 2.5 meters, and we've already taken 1 T into account. We'll take the next T into account on the short pipe with the pump set on it. So let's go back on our So what did I say it was? Sorry. What was the length? I didn't. Did. There it is here, 2.5. So if we say 2.5, and then on top of that we've got one elbow. Take that away. 2.5. So if we say 5 on that. And then the short pipe to the pump sets. So we've got lots of gadgets around the pump set. So if I go back to the AutoCAD and we enter this more or less this. In reality, all of the gauges are more or less, and the floor switches are more or less all on the flat. So we've taken that 2.5 with the elbow to here. So all of our gubbins, all of this lot is going to be effectively, see if I can be really clever about this, and half the screens. Of course, that was never going to work, was it? Well, it might be done. So it's only a short piece of pipe. It's probably 2.5 meters. So we'll hang on to that. I got shown a way of instantly splitting the screens, and it's never ever worked for me. Oh, come on, just let me grab that and move it. It's not going to have it, but I think I'm going to get away with it. So we've got a floor switch. Again, floor switch 4 meters for the floor switch. I'm going to write this down. 4 to the floor switch, and then we've got two isolation valves, which I'll guarantee, like I say, globe valves. 2 13s on top of that, which is 26. Then we've got the elbow at the bottom. We'll certainly have an elbow on there, so that's going to give us 2.4. And what else have we got? We've got non-return. Oh, there's a non-return valve. So non-return valve is going to give us 9. And that's it up to that gate valve. So if we grab all of that, open that lot up. So we've effectively got 2.5, 26 meters for the isolation valves, 2.4 for an elbow, 9 meters for the non-return valve. So you effectively got 40 meters of pipe there. We're back onto the short pipe, so that's 40. And then basically all we've then got is a short piece of pipe between the pump and the valve. Now I'm going to punch. There's a reason I'm going to punch that up to 50. It'll probably have to go higher than that, and that's probably 2 meters at the most, I'd imagine. So what we've now got, if we add all of those up, we've got a pressure drop of 4.14 bars, 4.2 bar or so. We've got a maximum flow of 116, and we've got a equivalent head of 42.2. So the next thing is we need the pump. So if I'm going to write that down because I'm it's 42.2 meters ahead, and we have 116 liters a minute. So now what I'm going to do, I'm going to pull onto these guys do sprinkler pumps. So lots of data in there, but what we really need is the pump curves, which is that. So if you look at the 703, so it's got total head there, and it's got flow here. Now we need 116, so it's nowhere that we can't get that. And to be fair, remember we're only looking at the residential. We know that the commercial is higher, it's around about 200. So if we take the commercial into account, we can't, we're looking at 250 litres a minute for that. That's not going to work. That pump's not going to work. Look at that one. That one would work for the flow, but if you look at 120 litres a minute, it can only deal with 10 metres ahead, and we've got 42. So that pumps out the question. Next page. So we're around 120. Oh, we're getting close now. So there is 120. Okay, we're under 116, but it's close enough. 120. We move up, and now that will only give us 38 metres ahead. I think that's a 32 force. No, 32 and a half, 35. That will only give us 37 and a half metres ahead. So you're looking at this pump here. So this pump will give 120 litres a minute, and it will deal with around about 49 metres ahead. So the pump to use will be the RZ 1005. So that would work for that. Just as a quick check, can it deal with 250? Which is the RZ 105, it's that one, isn't it? At 250, it can deal with about 15 metres ahead. It stands a chance. It might even need the Z106. But we'll do the commercial. We'll do the commercial in the session, because that's going to be really quick. So what's that? RZ 1005. And hopefully that makes sense. Now, what I did say I would do, was it on there? Hopefully that data is transferred. So there's that pressure drop, that 4.142. That was for CPVC. Now, if I used copper, that would instantly go up to 4.5. And if I used steel, which is the go-to for commercial, it goes up to 5.7. So you can see what a difference, hydraulic difference, the material of the pipe makes, and it's just purely the down to internal friction and how smooth that surface is. The other, I'm just trying to think what else we can manipulate in the spreadsheet. We could start going, right, okay. Now I know technically speaking, as you know from here, the bigger you go, if you look at the bigger you go, the more distance the more equivalency, pipe equivalency you get. So just if we start, I'm going to start doing is playing with the pipe sizes, and and you'll see what a big difference that makes to the head. But there's going to be a slight it's not going to be quite as good as it's going to show in the spreadsheet, because really we won't have taken into account the extra distance that's necessary on the linear pipes. But possibly what I would have done, certainly what I would have done for, and like I said, there was a reason why there was even that. Oh, it doesn't make a difference. I'm thinking if it makes a difference on that will end up needing to be 65, but that doesn't really make that much of a difference anyway. And if we went, instead of these pipes, we push these up to 40. Plant room 40. We'll go 40 all the way up the riser. That's the main riser. And the local riser, we'll leave that at 32. Let's see what difference that makes. Right, well that makes 4.43, but that was for steel. What I've got to do now is reduce that down. Let's change that for UPVC. So if I change that to UPVC, so that's almost a 1 bar pressure drop. You know, the previous pressure drop I think was 4 point something. So as you can see, it makes a big difference to you for the, you know, as it makes a big difference depending upon the material, and hence that's why CPVC is cheap and it's efficient, and it's basically why everybody uses it. There you go. Hopefully that makes some sense after the last, you know, probably 3 hours of running through something similar to this. Okay, catch you later. Bye bye now.